we're going to watch a video, and it's only 30 seconds. So you have to be very attentive to what's going on in this video. I'm only going to play it once at the beginning, and then if you need me to play it more, I'll play it more. But only once, and then we'll start having a discussion on it. Okay? Now, what unit are we in right now? What unit did we start this week?
Oh,
Chemical reaction. So what do you think you should have in your brain as you watch this video? You need to be thinking about chemical reactions. Got it?
Yes.
Yes? Okay, so let me play this video. How many seconds is it?
30 seconds.
30 seconds. Okay, here we go. Everyone's been doing this today, and it's been working really nicely, so hopefully it still works. Okay, here we go. You ready now? All right, and start.
5, 4, 3, 2, 1. And liftoff at dawn. The dawn of Orion and a new era of American space exploration.
Okay, what did you see?
A rocket
A rocket launching, yes. So, how does a rocket launch? With
with fire.
what does it need? Right? So, I need you to start thinking, what does this rocket need to launch? Okay? Now, I'm going to hand out an assignment. We're going to be working on this pretty much the rest of the period. Okay? Now, you actually need to draw this. Okay?
The rocket launcher?
Yes. Do you want me to show you the video again?
Terrible
Yes.
job.
Okay, it doesn't have to be perfect, just make sure it kind of looks like a rocket, okay?
But thank you.
You don't have a pencil, you need a pencil. So I'm giving you. Alright, so let me show you the video again, and then you can get started on drawing this model. But let me show you the video again, okay? Oops. Okay, here we go. Ready? So don't focus on the drawing yet, okay? Let's look at the video one more time.
5, 4, 3, 2, 1. And liftoff at dawn. The dawn of Orion and a new era of American space exploration.
Okay, so let's read the first part of this that we know what we are expecting. Okay? So follow along with me as I read this. So it says, think about the investigative phenomena video you watched. What was the science behind the phenomena you observed? To help you build an understanding of the phenomena, you will model it. A model is a tool that scientists use to represent an idea, object, or system, or parts of a system. Question: do you know what a system is?
Yes.
What's a system?
It's the focus of
The focus of what we're
observing.
observing. So what in this phenomena do you think is a system?
The rocket.
Okay, so keep that in mind. Okay, keep that in mind. Often, models are visual or physical representations, but they can also be mathematical representations or analogies. In this activity, you will make a visual model in the form of a drawing or a diagram. So what will you be doing? You're going to be drawing a model, okay? So let's look now at number 1 under develop and use your model. So SEP stands for Science and Engineering Practice. You can see the abbreviations back there. Develop models. So use the space to create a model of the investigative phenomena. As you develop your model, consider the following. So where are you going to draw your model? The box. Good. So let's look at that list. Make sure you treat it like a bullet list, like a checklist. Okay? So the first thing is, your model should show changes in energy and matter during liftoff of the rocket. So we already said the system is the rocket, and what do you have to focus on?
The lift
The lift off and what else? The energy and what's going on with the matter around it. Right? Good. Alright, your model does not need to include every feature of the phenomena. So do you need to draw everything you saw in this little 30-second video? No. Okay? So you do not need to include every feature of the phenomena. Instead, focus on features that you think are important for explaining how or why the phenomenon occurs. Give me 1 second, okay guys? Use labels to identify and differentiate the components of your model. So what do you need to use in your model? Labels. Make sure you're labeling everything. Choose an appropriate scale for the model. If needed, label any specific dimensions or measurements. Does anyone have any questions?
No.
Would you like me to play this again? Or do you think you're good?
Play again.
Play again? Okay, I'm gonna play it again. And then, imagine how this would have gone with a class of 30 students.
Dang, not that.
Pretty fluid.
You can use your finger, or I can give you a marker as a student.
This is sign.
Oh,
So no.
these things.
Alright, as you're looking at Leia's model, think about, is there something that you don't have that her model has? Is there something that you think the model is missing? And then we'll add to it as a class after she's done with her model. Yes? Yeah? Okay.
Burn is highly comprehensive.
Already I see some words I have not seen in previous classes. So that's
Stationary, build. Stationary. I have to think of that. I mean, technically it's not true stationary because the Earth is constantly moving, so we have kind of not true stationary.
Well, you have to think about the limitations of saying something stationary, because you're right, everything is always moving, right? Absolute zero is just a theoretical thing. So, there's always movement, that's right. But in terms of taking that into consideration, if something is staying still, you can say it's stationary.
Or it's staying still with regards to the Earth, right? So when
Right.
you get to physics, you'll talk about
It's usually it's just
frames of reference.
orbit. And if the sun, the Earth stops rotating or moving, it's going to make us fly at an incredible speed or something.
Right. But, there's that but, right?
Yeah.
Right now we're trying to focus more on the chemistry part of it, okay? But, it's good to think about those things. Now, a lot of the things you said before, I still want you to mention those here in a second, okay? So, Leah, do you have before, after, and then after?
I did it in steps according to the video as it played from what I see.
It's very interesting. I like your model.
You need a cell phone?
No, not a cell phone. Just, well, I hate to use this.
And also heat is producing heat all over the system. I mean, in the system because, yeah,
What are those the signs of?
thermal energy.
Reaction.
Yeah,
It
so,
also produces light.
okay, yeah, so if you want to list the signs of chemical reactions, we're running out of space. Hang on.
That's the issue. There's not
There
enough
you go.
space. There's not enough room.
We just made more room.
Okay.
Okay, so signs.
Wish we could do that on our paper.
I was gonna say, but we did not make more matter.
No, we actually did the law of conservation. We turned that matter, the fuel, into energy going upward, and also other energies too, like heat. I mean, thermal energy. Also, what else? Thermal energy, and also shock waves and sounds.
What are some of the signs of a chemical reaction that you just mentioned?
Odor.
Light. So there was a release of light, right? Temperature change.
Also, odor. I bet the fuel would smell nasty or something.
Okay, what are things that we can smell?
The fuel. Burning.
Right, but what?
The fumes.
The fumes. What's the word we've been using?
Gas.
Gases. Good. So,
We'll call them byproducts.
so we have a release of a gas, right?
That's why rockets are built to withstand the heat.
Release of gas, or odor. Odor. Okay. Anything else? Okay.
It doesn't seem to precipitate.
Where is the energy? How is the energy moving between the system and the surrounding?
Outward.
Exothermic.
Outward of the system, right? So what do we call that?
Exothermic.
So should we label this as an exothermic process?
Yes.
Right
It's very
there.
teeny tiny, but it's in the left
Oh,
screen.
it's right here. Okay, sorry, I did not see that. See, you guys see more than I do. Okay, so it's right here. It's exothermic. Okay, so don't forget this is an exothermic process. Anything else you'd like to add?
No.
Do you think we have everything we could possibly think of right now?
Yes.
Sure.
I have a question. What's the thrust pushing against?
Air.
Mm.
Oh well, actually, the thrust is pushing against gravity's force upon it.
Mm.
So the thrust is pushing against what?
Gravity. It's pushing
You
against
did?
gravity, and then fighting against air pressure because of gravity's influence on
It
air
is
pressure.
right there. Okay. Why didn't you mention it sooner? It's okay. I'm glad we mentioned it. Anything else? No? Do you want to compare your model to the other classes?
Sure.
Okay, this is yours. Yeah. Which I know we didn't end up labeling each one, but we try to label everything here. So let's look at what all the other classes did. So this is 5th period.
It looks like a jellyfish.
Does it look similar?
Yeah.
A little bit, right? A little bit similar. This is 4th period.
Whoa, looks like
That is a
a
lot.
sandcastle or something like when you're in the undersea water and you see a castle.
But you have a lot of the same stuff, right? It's
Yeah.
just every student has different ways of thinking about things.
In the middle, it's fuel and not O2.
Yeah, definitely. Okay, and then this was 3rd period.
And the moon.
Now, 3rd period, they were my guinea pigs. Okay, so they were the first class we did it with today. So we've been adding more, you know. Yeah. They really wanted to put the moon in there. They thought it was important to put the moon in. Okay. All right.
Well, especially with Artemis this week.
Artemis
Yes,
too.
yes. So they even asked, "Is that from the lunch last week?" And I told them, "No, it's not." It's
Historically,